Hello, can everyone hear me? Wait, let me just make a few changes. Then I'll change to full screen. So I'm going to be learning C++ again. Hold on. Yeah, last stream I finished chapter 17. It was about C-style arrays. The next two chapters are under construction, but I'm going to read them anyways. Okay, this chapter, iterators and algorithm, and this chapter, dynamic allocation. I'm going to read these two. They say they're under construction, but I'll just read them anyways. And maybe I will read some of function as well. I've already downloaded them 18, 19, and 20. And I will see how far I go. I'll just keep this open. Okay, so chapter 1, sorting an array using selection sort. A case for sorting. Sorting an array is the process of arranging all of the elements in the array in a particular order. Okay, sorting is generally performed by repeatedly comparing pairs of array elements or swapping them if they meet some predefined criteria. The order in which these elements are compared differs depending on which sorting algorithm is used. There are many ways to sort an algorithm. Selection sort is probably the easiest sort to understand, which makes it a good candidate for teaching, even though it is one of the slower sorts. Selection sorts perform these following steps to sort an array from smallest to largest. Starting at array index 0, search the entire array to find the smallest value. Swap the smallest value found in the array with the value at index 0. Repeat steps 1 and 2 starting from the next index. Okay, so we have 30, 40, 20, 10, and 40. So they will find the smallest number, which is 10, and put that at the first index. So they will swap 10 and 30. And then for the next one, they'll find the smallest integer in this selection, like from first index onwards. And then whatever smallest number they find, they will swap it. So for example, it's 20, they will swap 20 and 50. And then they will go to the next index and then they will keep doing this. So here's an algorithm. Let me try to make my own. So I keep forgetting so much. Uh, so they have std. Are they using std array or just C style? Okay. So int. Let's do float. Float array 10.2 1.5 0.0 3.2 1.2 4.2 and let's do 50.0 for int I is 0, I is less than, let's put a size over here. 1, 2, 3, 4, 5, 6, 7. Let's do 8. Wait. So const expression array size would be 8. Const expression 8, and then let's have 20.0. 1, 2, 3, 4, 5, 6, 7, 8. I is less than array size I plus plus. std. No, I'll have a print array function to see what my array looks like in between. Print array. Float array. And then array size. Is this correct? Hold on. Why is this causing an issue? Array size std cout. I'll have to do this for loop again. For loop, and then std cout. Oh, and it returns a void. Well, it doesn't return anything. std cout. std cout. Okay, let's just forget this right now. Let's just see if this works. Function from double to constant float. I can add f over here, right, to indicate that they are float. Okay, this works. Let's see, I want to do another thing. Um, how about if I do /t inside? So for this, and then let's do j j is less than array size, j plus plus, and then this starts with I. So hold on. Uh, int max is equal to array 0 or array I, and then this starts with I plus 1, and then this should be, maybe we should do it like this. mm, because if it swaps this, right, if it swaps a number here with a number here, these should be the last two swap, right? So there's no point putting I as this. Hold on, let me see. So int max array I, and then if array j is more than max, sorry, more than max, then we have to swap them. Int temp is equal to, we don't actually need max, we can just array I. Then like there's a 0 here, j, actually it has to be less than, so j is less than I, array index j is less than the element in index I, so we swap them. Array I is equal to temp array j is equal to array I. And let's see what happens. Initializing conversion from oh wait, float. You cannot assign to a variable that is constant. Oh yes, this is going to change. Okay, so let's see. Whoops. Temp is array I is array j. Damn. I think this should work. 0, 1.2, 1.4, 3.2, 4.2, 10.2, 20, 50. Yeah. So this here is selection sort. They did it some other way. STD size. Hold on. If I do const and std size, array. Okay, this works. They have std swap also. Std sort, because sorting arrays are so common. The C++ standard library includes a sorting function named std sort. It lives in the algorithm header. Std sort. They're using iterator for std size. So how is my std size working then? Lives in the algorithm header and can be invoked in an array like so. So sort std begin, so begin here and then end here. By default, std sorts in ascending order using the less than operator to compare pair of elements and swapping them if necessary. Manually show how selecting sort works on the following array. Wait, hold on. I need to do something. Rewrite the selection sort code above to sort in the descending order, largest number first. We just need this, right? Yeah, this works. This one is going to be difficult, but put your game face on. Another simple sort is called bubble sort. Bubble sort works by comparing adjacent pair of elements, swapping them if the criteria is met, so that elements bubble to the end of the array. Although there are quite a few ways to optimize bubble sort, in this course we will stick with the unoptimized version because it's the simplest. Unoptimized bubble sort performs the following steps to sort an array from largest to smallest. Compare array element 0 with array element 1. If element 0 is larger, swap it with element 1. Now do the same for elements 1 and 2 and for every subsequent pair of elements until you hit the end of the array. At this point, the last array in the element will be sorted. Repeat the first two steps again until the array is sorted. Hold on. So over here, you're swapping this one with the largest number. Actually, let's go back in ascending order. So we are swapping this one with the smallest number, and then we are swapping this one with the second smallest number. I think in bubble sort, how it works is you swap these two, and then we swap these two, and then we swap these two, until in the end we have the largest number. Now do the same. Repeat the first two steps again until the array is sorted. So we are taking the largest element and putting it at the back, and then we are taking the largest element and putting it at the back. So is bubble sort like selection sort in reverse, like in the other order? You're sorting from the back first, but in selection sort we are sorting from the front first. So index I is equal to 0. So 0 array size. Okay. For j should also be 0. J is 0 all the way till it should be array size minus I. So from 0 to, so this is size 8 from 0 to 7, and then in the next one it will be from 0 to 6, and then it will be next one will be from 0 to 5, and so on. So checking the first two and then swapping them, then 20 would be here, 10.2 would be here, and then in the next iteration checking these two and then swapping them. Let me think. Okay, let's run this and see what we get. Array 0, wait, j should be a 1. Hold on. I 0, 0 to array size -1. So 0 to 6. Yeah, the inner loop runs from, hold on, 0 to 6, and then it will run from 0 to 5. So 0 to 6, j, compare it with j plus 1. So we'll compare these two, and then these two, and then these two, all the way till from 0 to 6. So 6 and 7 will be the last one to compare. And then in the next loop, we will do the same from 0 to 5. So if the current one is bigger than the next one, we swap them. What is this? So when it was comparing 10.2 and 20, it put 10.2 at the front, which is correct. Put 1.2 at the front and 20 at the back, which is correct. And then 0 here, 3.2 here, 1.2, 4.2, 20. Why is this not 50? So at the last loop, it's checking 20 and 50. What's happening to 50 though? That's just weird. 0, array size -1. It's somehow checking this also. Like it's checking the thing after 50, and then it's swapping. That's what I think is happening. So int j is 0. J is less than array size -1 -1. So I is 0. I think I should be a 1. So let's see. It puts 50 at the back, and then 20 here, and then 10.2, 4.2, 3.2, 1.4. Yeah, this is correct. Okay. Should I print the ones in between as well? I think I should print it if the swap actually happens. Hold on. So let's see. It swaps 10.2 and 20. And then in the next one, it swaps 1.4 and 20 as it should. 0, 20, 23.2, 21.2, 24.2, and it stays there. And then it should print if the swap actually happens, right? So why did it this print these two? Oh, it's for this one. I should delete this. Is there any other question or add two optimizations to bubble sort? Okay, let's see. So it puts, yeah, it keeps swapping 20 until it goes at the back, and then it keeps swapping 10.2, and 4.2 is already set, 1.2 is set. It needs to put 1.4 at the back, and then it's done. Notice how with each iteration of bubble sort, the biggest number remaining gets bubbled to the end of the array. After the first iteration, the last array element is sorted. After the second iteration, the second to last array is sorted to, and so on with each iteration. So you don't need to, oh, I've already done this. If we go through, because I'm doing array size minus 1, and then j is less than array size minus 1, so I'm not looking at the last ones after they're sorted. If we go through the entire iteration without doing a swap, then we know the array must already be sorted. Already be sorted. Implement a check to determine whether any swaps were made this iteration, and if not, terminate the loop early. Oh, okay. So, swapped is initially false, but if any swap happens, I'll do it at the end. I'll do swapped is true. Swap is true. And if there was no, if none of the elements were swapped, then std cout early termination. And then break. Why is it going again? No, hold on. Sort needs to be defined here. And then if there was none of the element got swapped, then early termination. Okay, there is an early termination over here. So they put 1.4 at the back, swapping it with 1.2. Right. Now let's do 1.2. Let's do 12.2. There should be an early termination here. Now let's do an example of not early termination. So it's basically it's basically like this maybe. Yeah. So 1.2 and 0 was the last checking. So there was no early termination. Is there another question? Nope. Let's open the next chapter as well. Introduction to iterators. Iterating through an array of data is quite a common thing to do in programming, and so far we have covered many different ways to do so with loops and an index, with pointers and pointer arithmetic and range-based for loops. The examples in this lesson use a C++ feature called a class template argument deduction to deduce the template arguments from a template variable from its initializers. Okay. Pointers without pointer arithmetic can also be used to iterate through some non-sequential structures. In a linked list, each element is connected to a prior element by a pointer. We can iterate through the list by following chain of pointers. An iterator is an object designed to traverse through a container, providing in providing access to each element along the way. A container may provide different kinds of iterators. For example, an array container might offer a forwards iterator that walks through the array in forward order, and a reverse iterator that walks through an array in the reverse order. Although the appropriate type of iterator is created, the programmer can then use the interface provided by the iterator to traverse and access elements without having to worry about what kind of traversal is being done and how the data is being stored in the container. And because C++ iterators typically use the same interface for traversal and access, we can iterate through a wide variety of different container types using a consistent method. The simplest kind of iterator is a pointer, which works for data stored sequentially in memory. So array, 6 elements over here. So beginning is the first, the pointer, the reference to the first element, and then the end is beginning, the memory address of beginning plus size of array. For loop with pointer, so auto pointer beginning, oh wait, this is a memory address stored in the variable ptr. So as long as ptr is not the end, keep adding it, plus to move at the next element, then stdcout to get the value of the current element. You might be tempted to calculate the end marker using the address of operator using the syntax like so. So array std size of array, the reference to that. But this causes undefined behavior because std dereferences an element that is off the end of the array. Can't we do std array -1? Instead use array.data plus std size array. Data returns a pointer to the first element. So with this thing over here, let's see. So wait, hold on. Something is missing. Element undeclared by 10.5. Oops. Yes. Now, instead of end, let's do std size of array. Array, and then memory address of that. This should cause undefined behavior. and it doesn't. Hold on, let me see what's the. Why did they say it was wrong? STD size array. So why is this wrong? Yeah, after the same stream if someone can comment. Iterating is such a common operation that all standard library containers offer direct support for iteration. Instead of calculating our own begin and end pointers, we can simply ask the container for the begin and end points via member functions conveniently named begin and end. So array.begin, they give pointers, right? Yeah. Array.end, they give pointers. The iterator header also contains two generic functions, std_begin and std_end, that can be used. Std_begin and std_end for C-style arrays are defined in the iterator header. Include array includes iterator. Include IOStream, so std_begin, std_end. So is std_end pre-saved, or like are they calculating the end of the array? So when we do std size, does it go through each element, or is it like pre-saved from before? Is there like a member variable called size which keeps track of the size? Std array. Hold on. How can I check all the using size type? Let's see. I think the size is predefined. So it's not like C style array where we are calculating the size every time, but I might be wrong. In lesson 8.10, we noted that the less than operator was preferred over not equal to when doing numeric comparison in the loop condition. With iterators, it is conventional to use not equal to test whether the iterator has reached the end of the element. This is because some iterator types are not relationally comparable. Operator not equal to works with all iterator types. Back to range-based for loops. Array, int I array. Behind the scenes, the range-based for loops calls begin and end of the type to iterate over std array. Std array has begin and end member functions, so we can use it in a range-based loop. C style fixed arrays can be used with std begin and end functions, so we can loop through them with a range-based loop as well. Iterator invalidation. Much like pointers and references, iterators can be left dangling if the elements being iterated over change address or are destroyed. When this happens, we say the iterator has been invalidated. Accessing an invalidated iterator produces undefined behavior. Some operations run modified containers can have the side effect of causing the element in the container to change addresses. When this happens, existing iterators to those elements will be invalidated. Good C++ reference documentation should note which container operation may or will invalidate iterators. So we have vector v, autonom v, pushback, uh, when this invalidates the iterators of v, undefined behavior will result. Pushback num plus 1. Wait, let me see. Shouldn't this keep looping for infinity? Or maybe, hold on. I forgot what pushback does. Insert by moving into element at end. Provide strong guarantee. So it inserts into the vector. Hold on. Std cout v dot size. Size here is how many elements it has, right? Or no. Wait. Include IO stream. Size is 4, and if I do this again, it should be 6. So why does it say undefined behavior? Yeah, it's 6. You're pushing to the vector while you're looping in it. But it's looping through these 4 elements. And when you start the for loop, it's already predefined that it's going to loop through these 4. Even if you change the vector, I don't think the number of loops would change, maybe. Here's another example of iterator invalidation. If the elements being iterated over change address or are destroyed. So auto iterator we begin, move to the second element, prints to erase iterator, erase the element currently being iterated over. Plus plus it. Erase invalidates iterator to the erased element. So iterator it is now invalidated. So these two will cause undefined behavior. Okay. I think we need maybe better examples for for iterator invalidation. Like maybe if you're looping through this and then you decided to remove the elements. Uh, int counter is 0. Counter plus plus std cout std wait std cout. So 4 0 1 2 3 and then 6. Hold on. Let's do slash n, then slash n again. And then over here, let's do another slash n. Now, instead of push back, I'm going to remove from the end slash pop back. And then this should cause an issue. One, two, three. What is this? 257100. Hold on. No, wait, I see. Supposed to be a string. Now, now, so it does 0, 0, 1, 2, 3, and then 2. But wait, hold on. Um, shouldn't this output 1? Or should it be plus plus? Like that. Yeah, 1, 2, 3, 4. So it's going through 4, but there are only 2 elements. So this, I think, is a good example of daggling iterators. New programmers typically spend a lot of time writing custom loops to perform relatively simple tasks such as sorting or counting or searching arrays. These loops can be problematic both in terms of how easy it is to make an error and in terms of overall maintainability, as loops can be hard to understand. Because searching, counting, and sorting are such common operations to do, the C++ standard library comes with a bunch of functions to do these things in just a few lines of codes. Additionally, these standard library functions come pre-tested, are efficient, work on a variety of different container types, and many support parallelization. The ability to divert multiple CPU threads to the same task in order to complete it faster. The functionality provided in the algorithms library generally fall into one of three categories: inspectors, mutators, and facilitators. Inspector used to view data in a container, mutators used to modify data, and facilitators used to generate as a result based on the values of the data members. These algorithms live in the algorithm library. Use std-define to find an element by value. So stdfind searches for the first occurrence of a value in a container. Stdfind takes three parameters: an iterator to the starting element in the sequence, an iterator to the ending element in the sequence, a value to search for. So std, what does it return? It returns an iterator pointing to the element if it is found, or the end of the container if the element is not found. Okay, so std find, so this is the beginning, this is the end. Between these two, search for whatever, then check if this is equal to the end of the array. But what if it is at the end though? So if we are searching for 80, 80 is array.n, or maybe .n gives the position plus, like, right after the array. Override the found element. So found is it's a replacing, it's to replace the value. Use std find if to find an element that matches some condition. uh, Find if works similarly to find, but instead of passing in a specific value to search for, we pass in a callable object such as a function parameter or lambda, which we will cover later. For each element being iterated over, std find if will call this function, and the function can return true if the match is found or false otherwise. Here's an example of where we use find if to check if any elements contain a substring nut. So contains nut string view. Let's see what they're doing here. So string view for, so std array of string view, 4 elements array, apple, banana, walnut, lemon. So std find if array beginning, array end, then contains a nut. So I think you take a string like apple over here, then you use string dot find nut. Is this also in the this std string view find? Returns std string view no position if it doesn't find. Otherwise, it returns the index of where the substring occurs. So it checks whether these string exist or not. Okay. Using std count and std count if to count how many occurrences there are. So count if. Oh, so from here to the end, it checks how many times this is true. So how many times contains not returns a true. Also, I want to see what is array end. Hold on. Std array 1, 2, 5. Now let's do int, and then actually let's do 5 elements, 5, and then std cout array Begin. Is it like this? Shouldn't it be? Hold on. STD find. Um. Yeah, they're doing array.begin, right? Let's see. What's the issue here? So std say out doesn't work with iterators. Like I want to print the memory. Hold on. If I do this, auto begin, and maybe unused, end, and then end here. If I do debug, also I need to delete the other cpp files. So this, remove, remove. Then I should put this here. Where is the, like how do I check? Where are all of those windows where you check the memory addresses? Or this start without debugging? Using std find if to find an element that matches some condition. Oh yeah, we have done at this. Using sort to custom sort. So begin, array, and sort based on what the grade up. So 99, 90, 80, 40, 13, 5. Once again, writing instead of our own custom loop function, we can sort an array. However, uh, we like in just a few lines of code. So how do I check the memory? Wait, hold on. Let's see. Value 1, value end. Um, okay, I don't understand. So they're using custom sort and what else? Using std for each to do something to all elements of a container. So double number, so begin, end, double number. Okay, so it takes each element and does this with it. This often seems like the most unnecessary algorithm to new developers because equivalent code with range-based for loops is shorter and easier. But there are benefits to for each. Let's compare for each to a range-based for loop. With std for each, our intentions are clear. Call double number with each element of array. In range-based for loop, you have to add a new variable I. This leads to several mistakes that the new programmer could do when they're tired or not paying attention. For one, there could be an implicit conversion if you don't use auto. We could forget the ampersand and double number wouldn't affect the array. We could accidentally pass a variable other than I to double number. These mistakes cannot happen with std for each. Additionally, for each can skip elements at the beginning or end of the container. For example, to skip the first element of array, we can do std next, std begin, and then array end. Std next, array begin, and then array end. Now array is 1468. This isn't possible with a range-based for loop. Performance and order of execution. Many of the algorithms in the algorithms library make some kind of guarantee about how they will execute. Typically, These are either performance guarantees or guarantees about the order in which they will execute. For example, STD for each guarantees that each element will only be accessed once, and that element will be accessed in forward sequential order. While most algorithms provide some kind of performance guarantee, fewer have order of execution guarantees. For such algorithms, we need to be careful not to make assumptions about the order in which elements will be accessed or processed. For example, if we were using a standard library algorithm to multiply the first value by 1, the second value by 2, the third value by 3, you would want to avoid using any algorithm that didn't guarantee a forward sequential execution order. The following algorithms guarantee a sequential execution: for each copy, copy backwards, move backwards. Ranges in C++20. Having to explicitly pass array begin and array end to every algorithm is a bit annoying, but fear not, C++20 adds ranges, which allows us to simply pass array. This will make our code even shorter and more readable. I think an example of this would have been better. Next one is timing your code. I think I will end this stream after reading this one, and then I might start a new stream later today. When writing your code, sometimes you will run across cases where you're not sure whether one method or another will be more performant. So how do you tell? One easy way is to time your code to see how long it takes to run. C++11 comes up with some functionality in the chrono library to do just that. However, using the chrono library is a bit arcane. The good news is that we can easily encapsulate all the timing functionality we need into a class that we can then use in our own programs. So include chrono class timer. So std chrono steady clock. Second std chrono duration, std ratio 1. Okay, I need an explanation of what this does. M beginning. Oh, we do use the M prefix and wait, no. What is beginning? M beginning. What is this? So they don't initialize it anywhere? Oh, they do it here. Std chrono time point clock M beginning clock dot now. Double elapsed std chrono duration cast second clock down minus M begin count duration double std ratio 1. To use it, we instantiate a timer object at the top of our main function and then call the elapsed member function whenever we want to know how long the program took to run to that point. So timer t equal to time goes here. Now let's use this in an actual example where we sort an array of 10,000 elements. First, let's use the selection sort algorithm we developed in the previous chapter. So global array elements 10,000, timer class. Hold on. So initializing an array. And then IOTA, fill the array with values 10,000 to 1. Okay. Timer T sort array. Then the time taken. On the author's machine, 3 runs produce timings of 0 0.0507, 0 0.0506, 0 0.0498. So we can say around 0.05 seconds. Let's do the same test using std sort from the standard library. And this produces a result of 0.00693. In other words, in this case, std sort is 100 times faster than the selection sort we wrote ourselves. Things that impact the performance of your program. Timing a run of your program is fairly straightforward. But your results can be significantly impacted by a number of things, and it's important to be aware of how to properly measure and what things can impact timing. First, make sure you're using a release build target, not a debug build target. Debug build targets typically turn optimization off, and that optimization can have significant impact on the result. Second, your timing results may be influenced by other things your system may be doing in the background. Make sure your system isn't doing anything CPU, memory, or hard drive intensive. Well, I'm streaming, so I think that would count. Third, if your program uses a random number generator, that the particular sequence of random numbers generated may impact timing. Fourth, make sure you're timing waiting for user input. You're not timing waiting for user input, as how long the user takes to input something should not be part of your timing considerations. If user input is required, consider adding some way to provide that input that does not wait on the user. Uh, Measuring performance. When measuring the performance of your program, gather at least three results. If the results are all similar, they likely represent the actual performance of your program. Otherwise, continue to take measurements until you have a cluster of similar results. If your results have a lot of variation, your program is likely either being significantly affected by other things happening on the system or by the effects of randomization within your application. Because performance measurements are impacted by so many things, absolute performance measurements are generally not that useful outside of understanding how well the program runs on one particular machine you care about. On a single machine, relative performance measurement can be useful. We can gather performance results from different variants of a program to determine which variant is the most performant. After measuring the second variant, a good sanity check is to measure the first variant. If the result of the first variant are consistent with your initial measurement for that variant, then the result of both variants should be reasonably comparable. Okay. Okay, I will end the stream here. My plan is later today I will do dynamic memory. I wanted to do it this stream, but it's getting longer than expected. So I will end the stream here. And yeah, I'll see you next time. Bye.